Hi, Stephen.
Hi, Peter. Good to see you again.
You too. Welcome to the podcast on Everyday Metallurgy.
Thank you. Thank you for inviting me. It's great to be
You have
here.
been in, yeah, I invited you because I would like an episode on hard metals. And who else to bring than the man in Europe that has been developing and working on hard metals for, I think, the longest period, other than Stephen Mosley.
Yeah, I mean,
But
I've been doing
Stephen,
it for
will you?
years. Yeah.
Yeah, will you give an introduction of yourself? And I would like in that introduction to tell about your background. What is your educational background? When
Mhm.
did you find your call in metallurgy? And where are you today?
Okay, right. Yeah, then the story goes back to the coal and steel mining, coal mining and steel producing valleys of South Wales in Great Britain.
Mhm.
United Kingdom, formerly part of Europe, no longer, of course, since Brexit. But I was born in the 1960s, mid 60s in South Wales, to a community really that was reliant on industry,
Mm.
even though I was brought up on a farm. My grandfather was a coal miner and a farmer, and
Mhm.
yeah, I basically when I finished my schooling, and I was clearly tending towards science and engineering, science, technology, engineering.
Mm.
Um, I I was still or torn a little bit about going into medicine. Because
Mm.
that was the thing, and at the time, become a doctor, you get paid a lot of money, and
Yeah.
all this sort of thing, and looking into it and talking to people and whatever, it really wasn't my thing.
Mm.
So the next one on the list was medicine metallurgy, and it literally was a coincidence that I got into
Mhm.
metallurgy. Um, you know, there at that time there were not so many places doing pure metallurgy, so I chose Sheffield.
Mhm.
So in 1984, I moved to Sheffield as a young undergraduate student, ready to see the big city, having lived in a town, as I say, in the South Wales Valleys of 10,000 people. And
Yeah.
then suddenly I'm in a 500,000 city,
Mm.
center of the steel industry in the UK,
Yeah.
studying
Absolutely.
ferrous metallurgy for my
Mm.
bachelor's degree. And I loved it. I worked in the steel industry as an undergraduate in the summer holidays and whenever I could to get the experience.
Mm.
And then when that finished, I decided to do a PhD, and it was my first introduction to powders.
Mhm.
I did a PhD on the hot isostatic pressing of ceramic metal composites. So looking
Okay.
at interactions between oxide
Yeah.
ceramics, nitride, carbide ceramics, and nickel and cobalt based alloys,
Mm.
titanium as well, actually.
Yeah.
And it sort of changed a little bit towards joining of ceramics to metals in the end
Mhm.
by diffusion bonding. So a bit on the powder side and a bit on the solid state side, all using these high pressure, high temperature methods. And yeah, when I finished that, I did go back into the steel industry for a few years. But as the industry in the late 80s, early 90s was
Yeah.
going downhill a little bit. Uh,
Yeah, there was a movie about it, the Full Monty.
That's the one. That's the one. I mean, that was set in Sheffield. That was very very good. I
Yeah.
loved that film when it came out. So I mean, I'm based on a true story, obviously
Mm.
Hollywood eyes a little bit, but
Yeah.
yeah. So I saw the writing on the wall. I started on the manufacture of the casting molds, the ingot casting molds, which were then
Mm.
the raw materials that they then rolled. And by the end, I was working on the continuous casting and then the rolling. But
Mm.
it was just going down and down, So when the opportunity came, I saw a job advertised in a small hard metal company. I
Mhm.
guess we'll get to whatever hard metal is in a minute for all the viewers
Yeah,
that don't
yeah,
know what
yeah.
it is. But it was
Mhm.
an offer or a job opening for a technical manager with powder metallurgical experience, industrial experience. Yeah, I was
Mhm.
in, what was it, for late 20s at that time. And
Mm.
yeah, got the job, which was great. and was there for 3 years, watching also the decline of manufacturing generally in the UK. And so when Hilti in Liechtenstein, which is where I am now in the mountains, a bit higher up than the hills of Wales, so a couple of thousand meters higher, if you like. But when I got a call through the European Powder Metallurgy Association to apply for a job for a specialist in joining technology, hard materials, steels, and so on, and I thought, well, that's me. The job's written for me. And I got the job. And so 27 years later, still here. That's sorted. And it's amazing. And I've been involved in the European Hard Materials Group since its formation, which is now nearly 25 years ago. So I look a little bit different to what I did when I started. Time catches up with all of us. So but I've been the ugly face of the European Hard Materials Group for a couple of decades or so now. So
yeah, absolutely. And thank you very much for the introduction. I didn't know about that background either, so good learning.
That's the short version. Probably even my kids don't know that background, to be honest. Maybe my wife has already forgotten about it since we've been married for over 30 years as well. So.
Yeah. So are you Liechtensteinian citizen now, or
no? I even after Brexit, I kept my British passport, and I live in Austria, so I still live within the European Union. I kept all rights to live there, luckily. But I never became an Austrian, I could have moved to Switzerland and become a Swiss person as well, but naturalized. No. I'm fine. I'm a Welshman first, European second, and don't call me English.
Okay, but you have the accent.
My accent has softened over the last only 39 years since I left Wales. So there are hints of it left, but it comes back when I go home. That's it.
I could imagine. But I would like to dig a little deeper into the technical part now. Talking about hard metal, because many people really don't know what it is, and how they are made and what they are made of. So could you give an insight to the subject hard metals?
Yeah, I mean, how many days or weeks do we have?
I'll stop you if you go too far.
Okay. Now, I mean, hard metals, one of the very few words in English where the two words are stuck together. Normally we have a space between them, and that's because it comes from the German Hardmetall. And it was invented 100 years ago, this year, actually. The first patent was filed in 1923, granted in 25, license given, and products sold since 1926, 27. But it's one class of hard materials. And the hard materials goes everything from the high-speed steels and tool steels right up to diamonds. It's an order of magnitude in hardness values from, if you want, in gigapascals, 1 gigapascal to like 100 plus gigapascals on diamond. Hard metals are at the softer side. So the classical hard metal is tungsten carbide, it's sort of these triangular and rectangular grains here, with the cobalt, which is the darker gray. So it's another name for it is cemented tungsten carbide. So that the cobalt is the cement, it binds, it holds the grains together. So it is a composite, but it's a very high hard phase volume composite. So typically, majority of the grades are between 10 and sort of 20 volume percent of this metal. And so therefore 80 to 90 volume percent of this hard phase. That's the simple one. It still accounts for most of the or the largest proportion of tonnage, because things like the mineral extraction, resource tunneling, and drilling and so on uses these straight or very similar to this type of grade. So a lot of tungsten carbide and cobalt together. But for machining, and that's the bigger, really the biggest value within the hard metals, is inserts and things for machining and metal forming and so on. They use other carbides as well. So they could have tantalum carbide, a titanium carbide, niobium carbide, chromium carbide, vanadium, sometimes even some more exotics. So
Mhm.
it's a family, and this particular microstructure is only one of many. And in fact, I think they've been classified recently into 20 different types of hard metals, and so-called cermets. Another one of the early names, this which came from the French, was the ceramic and metal, because it's a combination of ceramic and metal.
Okay. Yeah.
Today we use the cermets for the carbon nitride hard phases. These are primarily the carbides. When we talk about the hard metals, it's a carbide.
Yeah.
So, like in this case, tungsten, one atom of tungsten, one atom of carbon combined to create this lovely crystal, this hexagonal crystal, which is why we have the triangles and the rectangles, because it sort of grows. Maybe those of you who've been to Ireland and seen the Giant's Causeway have seen the hexagonal basalt. That's what these crystals want to do as well. They want to create one phase or one facet which is like long and rectangular, and the other one which has a different shape. In this case, it would be hexagonal, but it's a so-called truncated prism. So it's not the perfect hexagon, but it's it wants to create something similar to that. So. But that's what hard metal is. It's a composite of hard phase and a metal phase produced by powder metallurgy. Obviously, that's why we're here. We're talking about powder metallurgy in everyday life. Yeah.
Mm-hmm. The binder phase, the metallic phase. You said cobalt, but it could also be nickel. Could it be something else?
That's correct. I mean, the original patent actually, interestingly, had the three main binder elements in it: iron, nickel, and cobalt. So it's the iron group metals are the ones that have the greatest, if you like, chemical affinity. They have the solubility of the tungsten and the carbon. They wet the tungsten carbide surface, which is what we need for sintering. And they have relatively good properties. Cobalt is still the best, but alloys of iron nickel or nickel iron, depending on the proportions, with some additives, can also achieve very good properties. And that is a trend. I think you've hit on a point here. Cobalt, scarce. It's being used a lot in batteries, so we know the price is very volatile as well, and it's going up, even though recently it dropped down again. It comes 2/3 of it from Central Africa. In some of the regions which are not so politically stable.
The war metal, it's also called.
Yeah, I mean, the Democratic Republic of Congo is the largest one, but also, I mean, it's being classed as a carcinogen. That it's likely a mutagen. It is toxic in respiration. It can skin irritations. The EU doesn't like cobalt. I get the sort of feeling. I mean, the European Chemicals Agency,
especially not in small powders.
Yeah, especially not in fine powders, exactly. But we need those fine powders for the properties. You can't cast this material. I mean, the melting point of tungsten carbide is approaching 2,900 degrees C. You can't just melt it. People do melt it for different purposes, but you change the structure, you change the composition, you change the properties. It is used in thermal spraying. There is fused tungsten carbide, but it's not then the pure monocarbide. It's then got other phases in the brittle subcarbides that you don't want. So for majority of applications that where you need the wear resistance, the strength, the toughness, fatigue resistance, high temperature properties, you want really the pure crystals of tungsten monocarbide, and you sinter those together. And one of the reasons it works so well is that because of the solubility. I mean, the tungsten and the carbon go into let's say the example of a cobalt binder, form this eutectic liquid. So we actually reduce the sintering temperature by almost 150 degrees just because of the compatibility, the solubility of the actual carbide phases in the binder phase in the cobalt. So
now you're deep into the process of how to manufacture it. Could we take one step back because you have powder? Are they could we call it singular powders? You have pure cobalt powder, you have pure carbide powders. You mix them in this 80 to 20 or 90 to 10 ratio.
Yeah.
And then you compact it, or how do you manufacture these?
That's right. I mean, you want to bring them into intimate contact. It's not just a mixing process, it is a so-called milling process. So you're forming them. It's not perfectly mechanical alloying where you get if you like, a complete mixing of all the phases. You still have the core of the tungsten carbide grains, but they are then mechanically plated, if you like, with the cobalt. It brings them into direct contact. And then from there, you then normally do a spray drying process, just like coffee granules. So you create your lovely flowable, pressable granules with an organic pressing aid, a lubricant in there. Could be paraffin wax, polyethylene glycol, all the usual PM organics or lubricants. And then from there, it's up to you what shape you want. You can put it in a die and press it to shape. From top, from the sides, there are now wonderful presses that can make all sorts of shapes that we couldn't think about it, even 5 years ago. You can use the plastic injection molding process, now called powder injection molding, because it doesn't matter really what's in it as long as it liquefies and flows. It's just carrying those particles and injecting them into a mold. So we can do that. We can extrude them. Die, just like squeezing something out of the toothpaste. And these days, of course, you can 3D print it in whatever where you want, whether it's a binder sticking the granules together, or you're melting them, spreading them like a hot toothpaste to create. There are many different ways. Also, isostatic pressing, cold and warm. So form the creation of the shape. Really, the method you use depends on what the final product is. But once you've got that shape, sorry, I'm talking far too much, as usual. So
I'm just enjoying it. And then you go to typical sintering.
Yeah.
And you said you could lower sintering with about 150 degrees.
Yes.
But exactly. What temperatures, what atmospheres are we talking? And when I look at the microstructure behind you, I don't see any pores. And typically, when you
will look closely,
compaction.
If you look very closely, you will see pores, but they are not pores from the manufacturing process. This material has been stretched at 800 degrees. It's been subject to a creep test. So just to see how stiff it is at that high temperature. So that we are pulling the microstructure apart a little bit. But these materials, because it's a liquid phase, the cobalt becomes liquid at around just under, let's say, 1300 degrees. Depends on the exact composition and whatever. But let's just take a house number 1300. Now, that's nearly 200 degrees lower than the actual melting point of cobalt. That is because it's the eutectic. It's because it's got the carbon and the tungsten in, which is diffused in the solid state. It's creating a eutectic liquid. So it forms this liquid much, much lower than it would do normally. We then would take it up. It has a melting range. It's not a melting point. So it has a melting range, another 40, 50, 60 degrees until it's fully molten. And then just to get that full densification, the particles rearranging, coming together, we normally take it up to around 1,400, 1,420 degrees. So, but as I say, it depends on composition. If you're using nickel, you go a little higher. Iron has a wider melting range, and you use a different strategy. But these materials normally will come out 99.98% dense. I mean, 0.02%. Is sort of the typical. And if we're using sintering with pressure, with the gas pressure, then we can eliminate pretty much all of. I mean, not just even the last fraction of a percent gets squeezed out. So these are fully dense materials, which is quite rare, as you say, for powder metallurgy.
It is, but how is the mechanical stability, the dimensional stability of it? Does it change geometry, or can you foresee it?
Yeah, it changes shape. I mean, obviously, when you press something with an organic binder in, quite a high volume fraction of the organic in there, it might only be 1%, 2% by weight, but it can be 10, 20 or more, and you can't compress these particles just by mechanical force alone. So we press a body that's between 50 and 60% dense. And then from there, it has to shrink. The remaining 40 to 50% has to close. So these parts shrink volumetric over 50, linearly around, let's say, 20%, 18, 20, 22%, depending on the manufacturing process. So to keep the shape, you're really so reliant on surface tension. I mean, we're very lucky that when the metals get liquid, they still want to keep together, if you like. So we are reliant on the intrinsic properties of molten metals in either a vacuum or hydrogen or other protective atmosphere. And we can achieve tolerances of less than 0.5% of the dimension. So for centimeter, we're talking 500ths or something. Really tight tolerances for something that's changing its size so much. It's amazing that these things come out, pretty much net shape every time. Yeah.
Quite amazing.
Yeah.
You said a little about where in what areas they are used or in which segments they are used. But if we should, if I should tell my mom where they're used, could you? I know chainsaws, the tip of a chain that could be hard metal. But do you have other applications in your daily life where you could meet it?
I mean, the first thing, just to expand on that, pretty much every tool you have that you put in a handheld saw or a drill has got a cemented tungsten carbide hard metal tip. So your hammer drills and your circular saws and your linear saws and so on. So everything that cuts and destroys material, either controlled or uncontrolled way, typically uses these materials. But even when you're all around you, you're unlikely to have much cemented carbide or hard metal physically within your grasp. If you're holding a ballpoint pen, the ball is tungsten carbide. So it's a tungsten carbide either with a chromium. Exactly, you've got one there. So that little ball is a solid tungsten carbide, all with a little bit of binder in, often chromium containing for corrosion because the inks are corrosive. But everything you're using has been in contact with a hard metal. So your mobile phone, the printed circuit boards now drilled with hard metal drills that are 50 to 75 microns in diameter, much finer than human hair. And you think how many holes are in those circuit boards. But just generally making things. I mean, every steel fastener that is around you, a screw or a rivet or a nail or something, has been made in hard metal tooling. Even the steel was rolled or drawn through hard metal dies.
The small rods in winter tires, for snow tires.
The spikes, exactly.
The spikes,
and the spikes, which are not allowed everywhere in Europe, which is a shame because I think there was some companies that used to make a lot of money selling tire spikes. But also, golf shoe spikes. You talk about spikes and walking stick tips and things like this. So that's where you actually physically have the hard metal in your hand or on your body. But it's just the indirect use of the hard metals that make everything. So you think of everything that has to be machined. And that's many things. It's not just metals; it's also wood. So all your furniture around you has been manufactured using hard metal tooling. You walk into your kitchen and your pans are being deep drawn in hard metal dies, and the stainless steel sink is rolled on hard metal rolls, and you can just go on and on. All the tiles that are made in hard metal lined molds because of the abrasiveness of the mineralic materials, and in your car as well. I mean, everything pretty much has to be machined or made or formed. So-called chipless forming, where you don't cut away material or machining. And every motor, everything that actually goes up and down or opens and closes using laminated iron silicon motors with wound copper wire. The copper's drawn through hard metal or diamond dies. Diamond dies are made using hard metals at high pressure. So and all this sort of stuff. It's everywhere. I mean, You could write a book on it, literally, of what it does, and yeah. All the plastics. I mean, plastics are made using compression tooling, pistons, cylinders, all hard metal. You wouldn't. I mean, we want to try and reduce plastic, but to actually make them, you need the hard metal.
Yeah. Okay. Then the big question is, you can make tools by cutting with hard metal, but how do you then cut a hard metal tool?
Yeah, everything. There's always somebody bigger and somebody stronger, and in this case, somebody harder.
Yeah.
So a lot of the manufacturing of precision parts or parts that require very special shape is done by diamond tooling. So diamond grinding, drilling, whatever. You can also cut them with electro discharge machining. So basically, which is a spark erosion technique. So even something like tungsten carbide that has a melting point, as I said, nearly 3,000 degrees, will still evaporate under the plasma. So you can use the wire cutting or die sinking techniques. What you try and do is whenever you can, you press it to shape and sinter it to shape. So you do as little as possible. Or you do it when it's in its so-called soft state. Now, the tungsten carbide particles, these things are always going to be 3,000 Vickers hard, 2,500, 3,000 Vickers in hardness. But when they press together loosely, they like chalk. They have the strength and the consistency of chalk. So you can actually, even with your fingernail, shape them. Yeah. So this is what's called so-called green machining. This is where you take a part that you've just either pressed, cold isostatically pressed, or usually or whatever, to create a preform. And then either in its state as it is, but usually in the so-called pre-sintered state, you heat it up to 600, 800, 1,000 degrees, where it just starts to create a little bit of strength to hold it together. Then you can machine it like anything else. It's just abrasive. So you use diamond tooling. Yeah.
Yeah. So. And now you just opened up to have an understanding. You said 3,500 Vickers, the hardness of the carbides. But if we compare with some of the things you work in, you said wood, you said steel, aluminium, tool steel. What are the hardness of that kind of materials, just to compare?
Just compare. Yeah, I mean, like I say, the tungsten carbide grains are 2.5 to let's say 2.5 to 3,000 Vickers. When you put that metal in, you typically then drop that hardness down, and depending on the size of those grains and the amount of this cobalt, you can even get down as low as 800 or 800 Vickers. Most of the hard metals are in the range, sort of, let's say 1,000 to 2,000 Vickers, just ballpark. The hardest of the steels is 600, 700, 800, depending on composition. There are some now which have got really, really high carbide contents. The high-speed tool steels, maybe 900. So we're always going to be higher than even the hardest of the steels. When you talk about the aluminium and the copper and so on, you're then talking 100. So it's an order of magnitude lower. So when we are machining wood, you think, wood, nothing. What can happen in wood? But natural wood contains silica particles. It contains resins which are actually corrosive. So the wear doesn't always mean it's because of the hardness of what's there. It can sometimes be chemical wear and corrosion as well. So we need hardness, absolutely, but we also need other properties of these materials.
Yeah. Then if we look into the future, will hard metals continue to be, now they're 100 years old, will we see hard metals still in 100 years from now? Or is there a competitor showing up?
We see a replacement, most certainly, of these critical raw material containing hard metals. So cobalt being replaced by nickel, tungsten being replaced by maybe titanium, carbon nitride, or niobium carbide, depending on application. The general hard metal family of materials will be around, I'm sure, for another 100 years. I mean, we are never going to make everything net shape. As long as we want to work materials and process things, we're going to need this type of material. So although we've seen substitution, they are generally substitution within similar classes of materials. And so this basic composite of a hard phase or hard phases and something that holds them together, the metallic binder, will be around for another 100 years. Of that, I'm absolutely certain.
Yeah, and I had a discussion last week with an expert within magnetic materials, and there we talked a lot about the Chinese dominance. How is the distribution on the manufacturing worldwide within the hard metal world?
Yeah. You hit on a point there. It's not just the manufacturing of the hard metals; it's the raw materials, the supply. I mean, the majority of tungsten comes out of China. Majority of tungsten comes out of China, so we are to a certain extent dependent on those. And they really are. I would guess now. I have to look at the statistics, so don't quote me on these numbers, everyone. But I mean, if Europe is around 16 to 18,000 tons, probably US is less than that. India manufactures quite a bit, and China is probably larger than any other single region. So I think there were some numbers, I don't know, 20, 30,000 tons, whatever it was. But you caught me off guard now. That's one thing I didn't look up. But no, they are a dominant force because they have the raw materials, and within their country they don't have the export tariffs, so we pay more to buy Chinese material. Then of course they have a price advantage, and also the energy and the labor cost. I mean, we're getting into much into politics as into engineering and science now. But yes, there is a very large amount of cemented tungsten carbide hard metal manufactured in China, and it's reaching, of course, regions such as Europe and the US and so on. That makes it sometimes difficult to compete in certain markets where it's low cost, low margins. And so that's why Europe is trying to innovate, and that's why we work. People like me have been working on this for 30 years to try and get things better and more cost effective and have productivity. And I mean, this productivity increase of a factor of 20 in the last 100 years has been entirely due to advances in manufacturing that have been supported by hard metals.
So if a little Stephen number 2 lives in a valley here in Denmark and is interested in the hard metal world, that could be a job for him in the hard metal world in Europe, also within the next 10 years.
Yes, absolutely. We've seen consolidation, of course, and a lot of the smaller companies have faded away. I mentioned myself 30 years ago in the UK. That company doesn't exist anymore. We've seen consolidation in many industries as well. It's just like the grain growth here. The large ones get larger and the small ones disappear. And that's really what's happening in the industry. It's consolidating to a number of major players. We're seeing acquisitions happening and bankruptcies. So, but there is absolutely, there are 5, 6, 7, 8 really good addresses to go to if you want a job in the hard metal industry in the next 10 years or longer. Absolutely. And you just got to hope they keep making them.
That's great.
Because they make the tooling for your cans. So your Danish beer, if you didn't have the hard metal, you wouldn't be able to put into your cans or even your bottles. So let's hope the industry survives.
I hope this will convince somebody to continue.
Oh, it's a fascinating field. Yeah, absolutely.
I fully agree. Stephen, I think I've got answers to all my questions.
I hope there's actually still somebody watching. I mean, we've been going on about 5 minutes longer or 10 minutes longer originally. But as I say, we could talk about this all day. It's a topic that has kept me academically interested, for 3 decades and more, and pays the bills as well, which is nice. But more fun. It's more about the fun, enjoying it. I'm a scientist at heart, and I've enjoyed it.
And I have always enjoyed talking to you also this time. And I hope if people who have been listening here are interested in learning more, they could contact you directly.
Me. Absolutely, stephen.mosley@hilti.com.
I'll put your email in the postscript of the video.
That's great. Yeah.
Wonderful, Stephen. Thank you very much for joining me today.
Peter, it's been a pleasure as always.
Thank you. See you.
Take care.
Bye.